Hey everyone, in this video, I'm going to go over the AATC worksheet 3 for 118B. So in this worksheet, I'm going to go over the practice problems and go over the detailed mechanisms or explanations, concepts behind them. So in this case, we have the reagent Br2 and an alkene. So what this reaction would do is that since we know the alkene is full of electrons, which means that they have a lot of negative charges, we could think of them as nucleophilic, and one of the carbons can attack the bromines of one of the bromines of the Br2, and as that happens, the alkene is giving up its electrons, becoming more positive or electrophilic, and as bromine is gaining more electrons, it's becoming more nucleophilic or more negatively charged, which then the bromine will come back and attack the other side of the alkene, kicking out the other bromine group there. Then our intermediate would look something like this here, where we form our bromonium ion. Here. And now, since we have this Br minus with no other competing nucleophiles, like no other water or alcohol competing nucleophiles, then this bromine minus ion will act as a nucleophile and attack either side of the bromonium ion and give us our product, where the bromines are added on opposite sides of each other or anti-addition from each other. Okay. So this carbon here, think of it as an SN2 reaction where we will invert the stereochemistry. The other carbon remains the stereochemistry of the wedge. And then we would have the enantiomer version of this as well. Okay, let's go over to the next problem. We see here, now instead of just Br2, we have Br2 with water. And this water here will be a competing nucleophile. So what I mean by that is that we are going to do the same mechanism here. As bromine becomes more nucleophilic and alkene becomes more electrophilic, the bromine will come back and attack that alkene, kick out the other bromine leaving group. And that gives us this bromonium ion here. And now we have a Br minus floating around and water floating around. And since we have water floating around, think of it as a solvent where we have a lot of excess water overpowering the bromine negative charge. So that means that the water group will attack instead of the Br minus group. Okay. That would give us this. So think of SN2 reaction where we invert the stereochemistry. We have the OH2 plus, and then this wedged bromine here. Okay. And then we could bring in our Br minus to deprotonate this positively charged oxygen of the water group. Okay, and then that's after our first step. Now let's bring in our second step of the NaH, and think of that NaH as a hydride ion, where this hydride ion will deprotonate the hydrogen of the alcohol. Bring this alkoxide here. So now we have a good nucleophile here, good electrophile here. This is going to be like Williamson ether synthesis from 118A, where this nucleophile will attack that carbon, kick out the good leaving group there, and then give us this product here, epoxide, plus the enantiomer version of it. Okay, let's go over the next problem here. So we have Br2 with water and an alkene. So this is similar to the last problem where we have a competing nucleophile, H2O. So let's go over that mechanism again. The nucleophilic alkene will attack the bromine. As the bromine becomes more nucleophilic and the alkene becomes more electrophilic, the bromine will attack the other side of the alkene at the same time, kick out the leaving group bromine there. Then that would give us this. Okay. And so to avoid steric hindrance, I put the bromonium ion as a dash to avoid that wedged metal group there. And we have a Br minus ion floating around and a water molecule floating around. So then this water molecule is the solvent, which is in excess and overpowers the Br minus. So then we're going to use this Br H2O to attack that carbon, kick out the bromonium ion there. And that would give us say this, and then this alcohol after it gets deprotonated, or it could have attacked from the other side of the bromonium ion and kicked off the bromonium onto the other side, giving us this product here instead. H. Okay. And also, this bromonium ion could have also been a wedge instead of a dash, like this here. And so if you do that same step again of the water nucleophile attacking from either side, that side or this side, then you would get these two other products here, where the bromine is now going to be wedged. And the methyl group of the ring will remain as a wedge because that remains unreacted. So this methyl group here remains unreacted. So here are our 4 products here. Okay, now let's go over the next problem. We see here that we have an alkene with Cl2 and no competing nucleophiles like water or alcohol in the solvent. But this is kind of a trick question, and I'll show you along the mechanism. So let's do the same mechanism here. The nucleophilic alkene will attack the chlorine as the chlorine becomes more nucleophilic and the alkene becomes less nucleophilic or more electrophilic. The chlorine will come back, attack the other side of the alkene, kick out the chlorine leaving group. And that would give us, say, this chloronium ion. Okay, and then we have the Cl minus group floating around. And we also have this alcohol group here, where this oxygen with the 2 lots of electrons can have a partial negative charge and act as a nucleophile. And we see that we could form a 6-membered ring. Here, 1, 2, 3, 4, 5, 6, because this 6 carbon here is electrophilic since it's bonded to an electronegative atom chlorine. So this oxygen here can attack that 6th atom, kick up the chlorine on the other side. Now we know we have a 6-membered ring here, where the first atom is the oxygen atom. So let's number this again. 1, 2, 3, 4, 5, 6. And then now we see what's attached to which group. This oxygen is still attached to the hydrogen at carbon 6. We see we have 2 methyl groups attached to that. At carbon 5, we see that we have the chlorine group here. And so the chlorine group could have also been a wedge instead of a dash, giving us the enantiomer product after we have deprotonated this OH plus with a base. So these would be our products here for that problem. Now let's go over the oxymercuration-demercuration reaction with the Hg acetate 2 water THF and NaBH4 NaOH water reaction. So whenever you see this oxymercuration-demercuration reagents and an alkene, in this case we do, we are going to add the alcohol in the more substituted side of the alkene. So we have 2 carbons here of the alkene. We have carbons 1, carbon 2. We see that this carbon 1 is more substituted than carbon 2. So we're going to attach the alcohol in this case because we're given water. So we're going to attach alcohol. If you are given alcohol instead of water, then you're going to attach an OR group instead of an OH group. But in this case, we're going to attach the OH group to the more substituted carbon, which is carbon 1. So our final product here would be this, where this was carbon 1, this was carbon 2. Okay, and that's the final product. Now let's go over to the next problem. We see here that we have an alkene, Cl2, and a competing nucleophile ethanol here. So then let's go over the mechanism here. This nucleophilic alkene will attack that chlorine. The more as that chlorine gains electrons, it gets more nucleophilic. The more nucleophilic it gets, the alkene gets more electrophilic. Then the chlorine will come back, attack that, kick out the leaving group chlorine. Then we get this chlorine. We have the chlorine minus floating around, or ethanol. Okay. And so now, since we're in acidic conditions, think of it as an epoxize. We want to attack on the more substituted side of the carbon because we want to see which carbon here would give us the more stable carbocation. Would it be the carbon that would give us the secondary carbocation or the primary carbocation? So since the secondary carbocation is more stable than the primary carbocation, this carbon here is the one that's going to be attacked by the nucleophilic alcohol, kick up the chlorine on the other side. Then that would give us this product here that oxygen still has a hydrogen, so that we can deprotonate that with the Cl minus to neutralize that oxygen. Then we can redraw this so it's neater. And it's enantiomer version of it. So those are the products of that practice problem here. So now let's go over to the next problem. So suggest a solvent and draw the structure of an alkene that would result in each of the following products when reacting with Br2. So we see here, in each of these cases, we have vicinal relationships between a bromine and an alcohol, or bromine with a bromine, or bromine with an alkoxy group. So we could infer that the carbons between them came from the double bond here. Okay, so we could draw that here. Let's say it's that. Okay. Before the vicinal bromine to bromine or alcohol or alkoxide are added, we have this, that. We have this, that. Okay. And so now we see here in the first case, this bromine is attached to an alcohol, which says that the nucleophile came from a water solvent. In the second case, we see that the vicinal groups are both bromines, which means that there are no other competing nucleophiles like water or alcohol, which means that we have a non-reactive solvent like CH2Cl2. And then, since in this case, the vicinal side of the bromine is an alkoxide, OCH3, an OR group, this gave them a ROH group or alcohol. In this case, the alcohol is CH3OH. So it is important on what kind of solvent you use. It could be a competing nucleophilic solvent, or it could be a non-reactive solvent like CH2, CO2, which will give you two bromines that are vicinal to each other. If you have an alcohol that's vicinal to the bromine, then your solvent is the water. If you have an alkoxide, OR, that's vicinal to bromine, then your solvent is a alcohol, ROH. Okay. Now let's go over the mechanism of the oxymercuration-demercuration reaction. So we know that this oxymercuration-demercuration reaction adds an alcohol in this case, because we have water, to the more substituted carbon, which in this case, the more substituted carbon is carbon 1. Yep, where this carbon 1 is attached to the tert butyl group, which is this tert butyl group here, and methyl group, which is that methyl group there, and carbon 2 is attached to 2 hydrogens, but now 3 hydrogens here, and the alcohol is attached to the more substituted carbon here. So now let's go over the mechanism of this. I'm going to label this tert butyl group as TBU to shorten the mechanism. Okay, so this is going to be TBU. We know that that's double bond there, H, and I'm going to draw out this mercury with the 2 acetate groups up here. So we know the acetate group looks like this. It's attached to a mercury. We know that it's attached to another acetate group because there are 2 acetate groups. Okay, and then the first step here is that the alkene will attack the mercury. As the mercury becomes more nucleophilic and the alkene becomes more electrophilic, the mercury will attack the alkene at the same time, kick out the good leaving group acetate there. Then after that, we would form a ring with the mercury, Hg plus, that's still attached to the one of the acetates. And then we know that this acetate here left as a good leaving group, and this is a good leaving group because this acetate is able to do resonance, and if it's able to do resonance, it will be stable, which makes it a good leaving group because it wouldn't want to react again. So now we are going to bring in our water here, which is our nucleophile. And now we have to see which carbon here of the ring would give us the more stable carbocation. Would it be the carbon that would give us a tertiary carbocation, or would it be the carbon that would give us a primary carbocation? It would be this carbon here that would give us tertiary carbocation, because if we break this open, we form a tertiary carbocation. If we break this ring open here, that would form a primary carbocation. We want to form a more stable carbocation, so we are going to attack on the more substituted side of the double bond or the ring. And then that would give us, say, TBU O H2, and oxygen has a positive charge because it has 3 bonds. And then we know that this carbon here is now attached to mercury with the acetate group. And then we don't have to draw in these 2 hydrogens because these 2 hydrogens of this carbon will be implied already. So then now we are going to deprotonate this alcohol to neutralize it. And that would give us, like this, TBU OH, this mercury here with the acetate group. Okay. And then now for the very last step, we are going to get rid of this mercury group with the acetate by using the second step of the reduction, reducing agent NaBH4. So whenever you see NaBH4, you think of a hydride ion like that. So I'm going to draw out the NaBH4, where the nitrogen, the Na has a positive charge, the boron has a negative charge. The hydrogen will have a negative charge, which will attack this carbon here and kick out the mercury group here. Mercury, kick out this whole group there. And that would give us TBU alcohol, and that carbon there, which is going to be this carbon here with 3 hydrogens. Okay, and also when this mercury group leaves, this mercury group will also kick out that acetate leaving group, giving us a mercury liquid and the acetate leaving group that left that can do resonance, making it stable. Okay.